just title indicates. Well, clique graphs and iterated clique graphs are defined differently, have two different concepts, but it was not known if they were equivalent. So it was an open question for at least 15 years. So the goal of this presentation was to show that they are really different. They are really different. Well, the definitions that we need are the basic ones. A clique is a maximal set of pairwise vertices. A clique graph is a graph that has the cliques of G as vertices, and two cliques of G are adjacent if and only if they are not disjoint. The operator is the function K that assigns to each graph G is clique graph, which is symbolized by K of G, and the powers of K are the functions obtained by composing K with itself. The nth iterated clique graph of G is the image of G under K to the n. So if we use this letter to indicate the class of graph, K of G is the denomination of the clique graph. K squared of G is equal to the class of second iterated clique graph, and so on. If we want to know what graphs are in these classes, we have a result for clique graphs. We have this characterization that says that the graph is in K of G if and only if there exists a Helly family F of complete sets of the graph which cover all the edges of G. Remember that the family is Helly when pairwise intersecting sets of the family have a common element. This is an example of a clique graph. We could take as a family that is Helly and which cover all the edges this one with 1, 2, 4, 1, 3, 4, 2, 3, 4, 1, 4, 5, and 2, 6. And we could see how the edges were covered with this family. But things get more difficult when we consider the other classes of iterated clique graph. We have no characterization for those classes, and that makes it difficult to answer this question. Is K of G equal to K squared of G? Well, what I am going to do now is to show that there is a counterexample of a graph that is in K of G, but is not in K squared of G. It helps to know that a graph is in K squared of G if and only if the intersection of K of G and the preimage of the graph under the clique operator is not empty, as this picture shows. Now remember that a graph is clique Helly if the family of its cliques is a Helly family. We have a result that says that clique Helly graphs are clique graphs because that is a direct consequence of the characterization of clique graph that I showed previously. What this tells us is that any counterexample that we want to find cannot be the clique graph of a clique Helly graph. It has to be the clique graph of a graph that is non-clique Helly. The easiest example of a graph that is not clique Helly is the pyramid. But unfortunately, we consider the clique graph of it. It is a very simple graph that is in K squared of G, so this is not a counterexample. But if we add some new edges, the resulting clique graph is different, it is more complex, and this graph is just the counterexample of a graph that is in K of G, but is not in K squared of G. If we look at these graphs, each vertex is adjacent to all the vertices except one. That exceptional vertex is called the opposite. Any class of graph with this characteristic is called an octahedral graph. That is the reason for the O in the names. And for example, to denote opposite vertices we use a prime symbol. For example, the opposite of 1 will be 1 prime. So for example, we could rename the vertices of all 3 as follows: 1 prime, 3 prime, 2 prime. Well, what I said in the previous slide, to prove that this graph is not in K2 of G, we have to prove that K of G intersection is pre-imaged by the clique operator is empty. We already know that it is a clique graph. Well, first we need to investigate what the pre-image of O4 under the clique operator is. And we have a theorem to characterize it. It says that if a graph G is in K-1 of O4, then O3 has to be an induced subgraph of it. So if we take a set V prime that induces O3 in this graph, and for each triangle, there are 8 triangles in this subgraph, we take a clique of the graph containing each triangle. The result is all the cliques of the graph. This allows to construct all the graphs in K-1 of O4 in the following way. We start with O3, and if we want to add new vertices, we need to define what are the triangles of O3 such that they contain all the vertices are neighbors of this added vertex. These triangles that we have to choose must be at least one, but not all the triangles. And finally, we consider 2 vertices that were added, and we want to define if they are adjacent or not. We have to see if the neighborhood share the vertices of one of the triangles of O3. Let's see this more clearly with an example. O3, suppose that we want to add just 2 vertices, 7 and 8. Suppose that we want to make 7 adjacent to the vertices of these triangles, 8 to the vertices of these triangles, and then it turns out that 7 and 8 are also adjacent because the neighborhood share the vertices of this triangle. So finally, this is a graph in K-1 of O4. This type of construction allows to prove some properties about these graphs in K-1 of O4. So we again take a set V prime inducing O3. We can prove that no vertex of the graph has all the vertices of V prime as vertices or as neighbors. And if 2 vertices have the same neighborhood restricted to V prime, they will have the same neighborhood in the whole graph. And if we take U and V adjacent vertices, and W another vertex that is in V prime, then we can say that either W is a neighbor of both, or W prime, its opposite, is a neighbor of both. Well, if we want to prove that K-1 of O4 intersection K of G is empty, we can do this proof by contradiction. We suppose that there is a graph G in that intersection. So, if the graph is a clique graph, we can take a heavy edge cover F by complete. And since it is in K-1 of O4, we can take a set V prime consisting of vertices A prime, B prime, C prime, inducing O3. For each triangle of this induced subgraph, triangle X, Y, Z, we will take a vertex V sub X, Y, Z that is characterized by the fact that it is found in each member of F containing the edges X, Y, X, Z, and Y, Z. This vertex always exists because the family is supposed to be healthy. It is simple to deduce that 2 of these vertices are adjacent, or they could be even equal if their subscripts have 2 common vertices in them. For example, B sub ABC and B sub ABC prime are neighbors because both are in each complete of F containing the edge highlighted the common letters in the subscript in blue so that it is clear to see. And this is something that I do in the other slides so that it is easier to follow. Now we define this set C of Fb prime consisting of the triangles of the induced O3 such that there is a member of the family containing this triangle. For example, suppose that we have a family with these sets, then the triangles that are contained in members of this family are ABC, which we can see here, A prime BC, also here, and A prime B prime C prime. Another property is that every vertex B sub x, y, z is adjacent to the vertices in its subscript, and graphically that is indicated with the vertex in the center of the triangle that is associated to it, arrows going to the vertices of the triangle that are colored in green. Moreover, if there is another triangle that shares a side with this triangle, and this triangle is in C of Fb prime, then what is possible to prove is that this vertex that is exactly one that is not in the common side is also an angle. That is something that we will use later. Now we can wonder what C of Fb prime can equal, and there are really a lot of possibilities. As you can see, there are many types of sets. The proof shows that each of these possibilities lead to a contradiction. And I am going to speak only about 3 of these cases. The castle, which are 3 triangles around another triangle. The umbrella, which are 3 triangles, and 2 of them doesn't share vertices, and the round that are all the triangles that share one common vertex. I choose to speak about those 3 cases because they summarize very well all the techniques that the proof uses. Well, the case of a castle is the most easy of them because if we have this castle in C of Fb prime, then we can see that the vertex B, A prime BC is adjacent to all the vertices of B prime, but there was a property that we have seen previously that said that it was not possible. Yeah? There is the contradiction. Now we can consider the case of an umbrella. For example, we have the vertex B A B prime C, which we can see that has the same vertices as C. Then, for example, we are interested in some neighbors of B sub A B prime C prime. We found some of them, but we also have that this vertex is adjacent to this vertex, and that makes B sub A B prime C prime also adjacent to C. This color green is to highlight what the reason of this statement is, and it will also be seen that I highlight some things in the next slides for more simplicity in following this. So as a conclusion, we have that this vertex has the same vertices as B prime. Then we have to continue to do this for some more vertices. For example, B A prime BC has the same vertices as C. B A prime BC prime has the same vertices as A prime. And B sub A B C prime has the same vertices, the same neighbors as A. But if we look at the 2 vertices of the list, they are adjacent, but we have that this vertices have the same neighbors as A and A prime, so this leads to a contradiction because A prime cannot be adjacent to A by the definition of opposite vertices. So we have the contradiction from the case of an umbrella. Finally, for the case of a round, we also find neighbors for these two vertices. We also note that these vertices are adjacent, and we use one of the previous properties that say that if they are adjacent, then C, which is a vertex of B prime, or C prime is a neighbor of both vertices. If this case holds, then we find that this vertex has the same neighbors as A prime because of this. Otherwise, we have that the other vertex has the same neighbors as A prime. Suppose that this is the true case, then we replace A prime by the vertex that has the same neighborhood as it, and we get another set inducing another O3 in the graph. And if we compare the sets C of FB prime and C of FB prime prime, we have that this triangle and this triangle stay because there was not a significant change while you replace this vertex by this vertex, so these ones were not affected. But this new triangle appears because of the definition of this vertex. So we have an umbrella, and we know by what I had explained before that umbrellas lead to contradictions. Well, the other case, because we have two cases, is very, very similar. We have another umbrella. Well, we have to continue by discarding all the other possibilities for C of FB prime, and the most suitable way to do it is by following a decreasing order for the number of triangles that the set C of FB prime has. Some cases may depend on others. For the proof I made, the relationship between cases is established by these diagrams. Well, after all this was said, there are some questions remaining. It is interesting to wonder if the iterated clique graphs of O3 provides all the examples to prove that the classes of the form K to the n of G are all different. But, well, we don't know. Perhaps some of them could be equal. And another thing that is interesting is to see what this class of the intersection of all the sets K to the n of G equals. Well, that could be the subject of a future work. That's all.
I'm trying to show infinite family, not trivial. I mean, what I mean is non-trivial. You know that the octaedron is in the difference.
K of the octaedron.
Yes, the difference. But you are trying to show another graph in this difference.
I have not still found any other graph. I tried with one graph, and it turned out that it was in K squared G, and really I didn't continue to research another graphs. I think that now I would prefer to find graphs in the other difference. For example, a graph in K squared G minus K cubed G. But it is possible that by chance one could find another graph.
I mean non-trivial that does not contain the K of
It is fairly open.
Pablo, because it was so difficult to find one in the difference that it would be nice to know more properties about the structure of such a graph.
Yes,
Maybe
yes,
that's
it was,
what you
it was
have.
difficult with O3 and O4. As the clique graphs of O3 grow exponentially, perhaps the complexity of these pros also grow exponentially. Who knows? I will try in some days or some weeks. Yes.
You say it's 25 years for the problem, yes?
I don't remember saying 25. I think I say 15, but I am not really sure on that number. I say I know people that was trying to solve this 15 years ago, but that doesn't mean that there was another people that I don't know that was trying to solve this too. I think that there was really people thinking about this problem. Perhaps they did not work too much on this, but they thought at least about that, because this problem is, I would say that it is simple to state. I would say that when one thinks about theoretical problems about big graphs, this is one of the first that could come to mind.